This, as you heard, is a joint talk by myself and Laura Voinea, and is a joint work with Dominic Orchard, and we are all based at Kent. It's about indeed protocol engineering for communicating actors. Imagine that you are trying to build a distributed systems that is made of a number of actors. And actors do basically two things. They do some internal computation and communicate with each other. In this talk, I will discuss the advantages of modeling the communications part between actors using precise protocols, which here in this talk we intend as some sort of models of communication behavior. We will see how these protocols can be used in the programming practice, so how they can be linked to programming languages and code. And at the end, I will introduce a framework we are working on about protocol engineering. So to start, modeling behavior. So an example of behavioral model of protocol is a machine that is model with a formalism of finite state machines. You may be familiar with it. A finite state machine is made of a number of states, and then there are actions from each state that lead you to another state. And by using this kind of models, we can model the control flow of some code. Then we can map these models into real code. So for example, on the right-hand side here, I'm trying to implement the same example. This is a telecommunication examples, by the way, that I took from a Lang programming book of a telephone, where I'm modeling the idle state as a function. So I invoke the idle function when I'm in the idle state, and then I'm waiting to receive some of the actions that I can receive from that state. And as a reaction, I go to the new state, ringing or dial, depending on the action I received. And this is just a skeleton of the code. So it's how the control flow should behave. Then, of course, I can expand my code by having some internal communication and also model some data flow that goes through the states. So here we are just modeling actions and states, but actually the focus of this talk is interactions. So as actions, we intend communications, so send and receive actions between distributed actors that communicate asynchronously. And one example one such example is given here, is the bank server. And as a formalism we can use to model this distributed system is an extension of finite state machines. It's called communicating finite state machines, has been introduced in 1983 by Brandon Zapiropoulos. And this is an extension. You see, it looks like a finite state machine, but you see that in the edges, each action has either a question mark at the beginning or an exclamation mark. A question mark means it's a receive action. An exclamation mark, it means it's a send action. So in this bank server, we are in the initial state as 0. The server offers the client two options: request for a statement or request for a payment. In either case, the protocol proceeds to a different state where the behavior is different. In one case, the server sends the statement data. In another case, it waits for further payment data. Okay, so this is a communicating finite state machine. And we can map this into code very similarly. So every state is a function. We can add internal computations, data flow, and so on. When we use this kind of protocols, however, especially if we are focusing in the harsh asynchronous world, a scenario where communication is asynchronous, as in the case of Erlang programming, as in the case of web programming, in most cases, communication is asynchronous. And not all the protocols we may design with these good formalisms are good protocols. We may have bad protocols. So here is an example of a bad protocol. I slightly modified the server of the previous slide. I created a dodgy server. The server can do, this is the bank server modified, can do two things: either receive a statement as it did before, or can decide to just quit the session, sends logout and terminate. Now, if you wanted to consider the overall distributed scenario, we could add a client. So the most straightforward way to proceed would be to, well, take the same structure of interaction for the client. We just swap the direction of interactions, where the server is receiving a statement, the client will send a statement, and just we invert every send with a receive. Okay, so now we have a system of communicating machines with its own semantics. And let's see what happens if we execute it. So we have mailboxes, asynchronous communication via mailboxes. Actually, the formalism uses FIFOs, but it doesn't matter for the scope of this talk. So the dodgy server may decide to, well, send logout. It goes out immediately. The logout message gets placed into the mailbox of the client. Communication is asynchronous. The client may read the mailbox and react, or may be doing something else, maybe actually say, okay, I really need a statement now, and send a statement to the server. At this point, let's say the two nodes have gone out of sync with respect to the protocol, and we have a deadlock on the client that will wait forever for the statement data. Okay, so this is a protocol that is intrinsically bad. And of course, if you start building your code from a bad protocol, you're very likely to produce a bad program that suffers the same deadlock issues of your protocol. So we want, first of all, to characterize what are good protocols. And unfortunately, there is a negative result that was published in 1984 by Gauda, Manning, and Yu. And in general, given a system of finite state machines that communicate asynchronously, it is undecidable. I cannot tell you in general if the system is safe. And here by safe, I mean free from deadlock and free from unspecified receptions. That is when you receive something you're not expecting. Okay, so we have a space of safe protocol, which we cannot characterize. We have this negative result. We can do nothing about that. However, the same authors also defined a subclass of safe protocols, a smaller class, which respects the three constraints in the way interactions are structured. I will not go into the details here because of time constraints, but there are these three constraints: deterministic, non-mixed state, and compatible. In the previous example, just for mention, the problem is that there were mixed states. So if you avoid these three problems, these three issues in your protocol, then you are sure to have a safe protocol. Okay. So now I intentionally also not go into the details of this because we do not expect you to remember all of this. So I already told you that there is not a perfect characterization of safe protocols, but theoretical computer scientists are trying their best to work and enlarge this pink bubble to make it as large as possible, to capture as many good protocols as possible with finer and finer sets of constraints. Of course, we do not want developers to go and read all these research papers. We would like them not to have to do it by hand. So that's how we come to building the theories into tools so that you have a support for that. And this brings us to the second part of my talk. One way in which we can build this knowledge about how to build good protocols into tools is by using session types. So session types is a technique that has been introduced in the early 90s. And basically, it extends the notion of data type to communication structures. You're not just type checking a program, checking, for example, if it's supposed to send an integer, that it really sends an integer, but you're also checking that the flow of interaction structures respect a specific protocol. For example, with session types, I could design a server as an entity that first receives an integer and then follows up by sending a string and terminate. There are more complex constructs with session types. So this is a very simple example. Then when you want to create a client for the server, as we have seen before, you take the same interaction structure and you swap the direction of the interactions. You create, in the session type jargon, it's dual. And this is just types, a skeleton, a skeleton of interactions, it's not programs. What you can do later, you can actually develop code that implement these protocols. Here, for example, for implementing the server, I receive the integer that I put in the variable a, and then depending on the size of a, I send back the specific string, small or big. So I actually say what is the integer, what is the string, and so for the client. And I can statically type check the program against the session types, and this gives me basically two things. Gives me conformance to the prescribed protocol, and also safety. So session types have built in already these 3 constraints that give you safe protocol. So if you scribble things by using session types, you are sure you're having good protocols. And by type checking programs against session types, you have safety also in your code. Okay. So you have a non-specified receptions and no deadlock that reflects from protocols to code. Initially, session types were defined for a static type checking, but there have been in the years work about using them for runtime monitoring, API generation, or even using them to optimize supervision strategies for Erlang. Now, the project we are working on now, Laura and myself, together with the University of Glasgow and Imperial College London, is about using session types to enhance the recovery strategies of actor systems to have them even more reliable. The project is called Stardust and will go on for another 3 years. But the point of focus of this talk today is something partially related that we are developing at Kent together with Dominique that you see here in the center. And it's about engineering protocols and then reflecting all this engineering into code. To give you a context, I would like to implement a banking protocol. We have already seen a banking protocol. What you see here, this SB, is the session type version of the server that we have seen earlier on with communicating finite state machines. Basically is a banking protocol that receives a request for a statement, a payment, or a logout, and then proceeds. And this MUTI is just a recursion that, and the T goes back to the recursion. And I would like to, of course, have authentication. Once we have banking, we would like to have authentication. And SA that you see here on the bottom is an authentication protocol that requests a PIN, then determines whether the PIN is correct, in which case sends back OK, otherwise fail, and then proceeds with the TAN authentication. I would like to compose banking and authentication in a specific way so that, for example, the user is offered the menu of the bank, statement, payment, and so on, only after a successful PIN authentication. And for payments, we would like also on top of that a successful TAN authentication. Okay, so we want a system where we can describe these constraints to appropriately compose and engineer protocols. We would like to lead to implementations that reflect all these properties. And also we would like later to make it easy to re-engineer. So if I want to re-implement banking with a different kind of authentication, I would like to have some support with that. So now let's break the problem into smaller pieces. The first problem is defining what's a good composition for protocols. And we have seen in the previous slide that we would like to steer the composition in certain ways, so that, for example, the authentication comes before accessing the menu. And in order to do that, we have added to protocols assertions. So we can annotate protocols with assertions to define contact points between protocols. We have 3 kinds of assertions: assert, that gives a guarantee; require and consume, that request a guarantee, and the consumer linearly removes the guarantee. So for example, if I want to compose a protocol that sends an item and a protocol that receives a payment, and I want to specify that I would like the payment to happen before dispatching the item, I can annotate the protocol with assertions and say, well, before dispatching the item, I require a receipt. And in the other protocol, I say, well, I issue a receipt only after payment. And I would like to have this notion of algorithmic notion of composition that, given these two annotated protocol, provides me only those compositions where all the requirements expressed by the assertions are honored. We call this property well-assertedness. We want that all requirements of the component protocols that are ad hoc and they are defined by the engineers get honored in the composition. And this is one property that we want, but there is more. So we went to a more philosophic problem of what is a correct composition. The second property is behavior preservation. So when we compose two protocols, we would like that the interaction structures of the composition does not violate constraints that are set by either of the component protocols. I make an example. Here, I want to compose a protocol where you buy a movie, okay, as a timely example, and one in which you watch the movie many times as you want, okay? If I compose the two, as you see on the right-hand side, so I basically merge the protocols and I put them into a recursion, I obtain an object that will give you this kind of traces. You buy and you watch, you buy and you watch. In this case, you see that you are buying more than one time, and this is not an interaction structure that is described by the protocol on the right-hand side, that where you always buy once. A correct way instead to compose by preserving behavior is to first have the buy and then have the recursion. Okay, this may seem trivial, but we need to embed them into an algorithmic notion of composition, so to make sure that we always get it right. So preservation, we do not want to introduce behaviors that were not foreseen by the initial protocols. Fairness, this is the other way around. We would like that no component protocol gets neglected when we do the composition. So again, if I want to compose the watching movies with the buy a movie, if I compose the protocol by saying, okay, I'll watch as many times as I want, and then I buy, I may have traces where I never actually pay for the movie. Again, correct way is you first pay and then you watch repeatedly. Okay, and this again, the first composition is not a good composition because it violates fairness. You don't honor the buy part of the protocol, and the second one is a correct one. Okay, so fairness. However, this kind of fairness is good in certain circumstances. In some other circumstances, it may be a bit too strict. Now let's think of a scenario like the one we have seen in our Pintan banking example. So we have an authentication protocol that receives a password, then reacts with either OK or KO and asserts, good, you got the authentication only in the case of OK. And then we have a banking protocol that requires authentication. Now, if we wanted fairness, we couldn't really be able to compose these two elements because, well, if we composed the two protocols, as you see here, that you have the banking only in the case of correct authentication, well, we have that in some branches, the protocol banking is neglected. So we also introduced a notion of weak fairness, for which all component protocols can proceed until they terminate in some execution. This is a weaker form, and basically you use it being aware of what you're doing. Once that you see that fairness produces no results, you see whether this is acceptable. You may want to weaken the fairness condition. Problem 2. So we have seen, we have captured all these aspects into a definition of composition. We have an algorithm for it. How now to make it easier to re-engineer protocols and code that derive from these protocols. So now, here we have the bank and pintan protocols that I have already asserted for you. I have annotated with assertions. We have produced a library that composes protocol automatically. So you would obtain something like the protocol you see on the bottom of the slide. You see, it's not entirely trivial to do it by hand. It would be a bit error prone. And once you have this composition protocol, we have a library generate that creates a stub, like a skeleton of interactions using Erlang, the state machine for Erlang. And this is just the perspective of a node. So assume now we have composed the bank and pintan, we have generated the stub, we have extended the stub with our own internal computation, and we have it into a node executed in a network. Now, assume we want to complete the system, we want the client as well. We have used session types as a notation for protocols, which brings us some good advantages. For example, given the protocol P, that is our pintan and banking together, we can derive the dual. Also algorithmically, it's quite easy. You take the same interaction structures and you swap the direction of the interactions. Then you can use this, this dual protocol to generate the code for the client. And thanks to the fact that we are using session types, their communication is going to be safe. So it's going to be deadlock free and free from unspecified receptions. So in summary, when you need assurances, we advise you to use safe protocols. And you don't have to do it by hand, but you can use theories built into tools for generation of code and verification. I presented a theory of protocol engineering that enhances the notion of what's a good protocol with what's a good composition of protocols. We focused on 3 properties: preservation, fairness, and well-assertedness that are guaranteed by composition. And Laura will show you now a tool that supports re-engineering and code reuse. Just a mention about related work. There is, as you see on the bottom of the slide, there is some related work about similar subjects, but the related work mostly do this composition dynamically via weaving, a bit like aspect-oriented programming for protocols. Instead, we focus on creating statically an object composite protocol that then we can use to play around and generate code and extract and so on. Okay, just a quick overview of the demo. So Laura will show you, you see here the Git link, a tool for the composition and also the decomposition of protocols, and for the generation from protocols to code using Erlang OTP, and particularly Gen state machine, and also for extraction of protocols from code. So the demo will go like this. You have a code, Erlang code for the pintan part, only the authentication. We can extract the protocol from it. Then, assuming we have designed on our own our banking protocol, we can use the composition function to generate the composite protocol. Once we have the composite protocol, we can generate now the stub. A human, we will not show it here, but can enhance the stub with local computation. And as a future ongoing work, we would like also to be able to migrate the code, the inner code of the pintan, all this computation part that humans have added to pintan to make it better than the stub. We would like to migrate it to the new composite protocol, and it should be easy thanks to the fact that when you use a Gen state machine, all your code is very tidy. And yeah, so I finished what I wanted to say, and I'll leave it to Laura. So I'll stop sharing the.
Thank you. Okay, so I'll give a quick overview of the tool that Laura introduced. So say we already have an implementation of the Pentan protocol represented as SA as a state machine written in Erlang. So here I have a stub of it, as you can see. We can then use the tool to extract the protocol from the Erlang code. So for that, we'll use the extract option and give it the file name. So this is going to return a protocol that is specified using a format that is right here, defined as a user defined type. That specifies an action, a branch, the three assertions: assert, require, and consume, recursion, and end. So having this protocol now, we can then go ahead and add any assertions that we might want to it. So here I already have the Pentan protocol already asserted, and we can use that to compose it with a different protocol. So I'll just use it to compose it with bank. So this is the equivalent of the SB protocol that Laura showed us earlier. So for that, we'll just use the compose. And here we have a third parameter specifying whether the interleaving is going to be based on a weak fairness condition or a strong fairness condition. So if we choose strong, as Laura specified previously, we're not going to get any interleavings. So this is going to be empty. If we, on the other hand, choose a weak interleaving, that's going to give us all possible interleavings. So I'm just going to paste the command here. This is going to give us a list from which the user can choose the interleaving the most appropriate to their purpose. So let's say that here we just choose the first interleaving and call it banking PT. So this can then be used to generate an Erlang state machine stub. So to do that, we'll use the generate option. Banking PT. And just banking. Okay, so this is now going to give us a stub where each of the action and branch and the original protocol, each of those will become a state. A branch will become state function with multiple clauses for each of the options that the branch offers. And if we want to obtain the dual to show the two different protocols, what we can do is add this R underscore or S underscore before the parameter of the action to specify the direction, whether that action is a receive, in which case we can add an R underscore, or a send. So in that way, by adding the required R's and S's before each of the actions and branches, we can obtain the two duals showed earlier by Laura. The assertions are now specified as comments above each of the states. So here we can see we have an assert pin and a require pin, same as we have in the protocol before recursion. This stub can then be extended as necessary by the programmer with the desired logic, and can then be reused later on or parts of it can be reused later on using the options of decomposing if we want to obtain part of the protocol specified here, composing, and extracting. So in the works, there's going to be automatic code migration, automatic assertion extractions, and hopefully some assertion inference. The code is available on GitHub, so if anyone is interested, I can post a link to it. Okay, I'll leave it here. Thank you.
Thank you very much. Very interesting presentation. We actually have plenty of time for questions. And as far as I can see in the Q&A, the only question is about, well, and just as I said, that another question appeared. There was a question about using this in a context relevant to Elixir. So is this something?
So it's something that could definitely be translated to Elixir. So as far as I've seen, though I've not used it that much, it seems like it could easily translate to Elixir as well.
Mm-hmm. We have a question from Felix. If you want to unmute and ask. I cannot hear you, Felix. Can anybody else do?
No.
You appear.
Can you hear me now?
Yes. Go ahead.
Okay, great. Thanks. Thanks for the talk. So actually, I wondered whether you chose the binary setting for the presentation only, or have you also considered the multi-party setting in your work? And could you elaborate on the challenges? Because I did some work on multi-party session types, and I see that there are like quite some challenges that you might face then. But in this setting with the composition, that sounds interesting.
So the composition per se is sort of orthogonal to multi-party or binary. Actually, in the paper we are writing, it's general. So we leave it to parametric. So you may extend extend the syntax, just the syntax, and have say A, B before the name of an action to signify that it is a node A that sends to node B, and so you have multi-party. In that case, you would have a multi-party protocol from a local you would have sort of not a global protocol. You would have a local multi-party protocol. So there, the issue would be to synthesize all the other participants in the right way. Yes. We were working on example. We didn't have time to show. For example, if you have a user and an instrument that follow some dual binary sessions, and then you want to add in the middle a proxy. This proxy would implement one side of one session and one side of the other session interlinked together. There you can use multi-party to extend these and then to bring it back to the other participants. This would come quite easily. We didn't check more examples about that. In principle, it's doable. The challenge, I think, is when you want to create the other participants, then you have to discern the roles. Yeah.
Mm-hmm. Thank you. Kiko also has a question. Would you like to ask it in person?
Yeah. Hi. So I was wondering if you require the program to be fully typed in order to be able to execute this tool, or if there's some kind of support for some kind of gradual typing or something like that.
Okay, so we do not do. Oh, sorry. You
go ahead.
No, you go ahead.
So one thing to say that we support non-typed programs because what we're using is the structure of the state machine to extract or generate code.
Okay, thank you.
Mm-hmm. We have another question by Julius. Would you like to ask in person?
Yeah, sure. Are you aware of such a language, TLA plus? It's it's all similar purpose. It actually can be used to design protocol and check if it's, it doesn't have deadlocks and you have fairness properties and stuff. And is your work related to that, or is it a complete different?
Our work is coincidentally based on session type. So the first problem we got is, well, let's try to define what composition of protocol is. And we stuck to a syntax. And since we were there and we are working on session types and there are these nice advantages of the dual, we used that. I haven't considered DLA plus, but yeah, I'd like to have a look. It possibly, as I said, is parametric, the language, so it may be accommodated, but I don't know right now.
Well, in my opinion, in some kind of way, TLA plus is much larger than your work, and in some way your work just improves on TLA plus possibilities because you have a code generation and code stub generation. TLA plus is simply the tool of proving algorithm correctness, and it has a different language than Erlang, so that's.
So for what I understand, so DLL maybe something, so session types is something we build on, right? So it's not our work. So we use the session types, so we added this composition and generation part.
I see. Okay.
And the same possibly could be done with DLA plus. From what you say, I understand it seems a more general tool where you can prove more ad hoc properties in the sense that you can define specifically what properties you want the system to.
Yes. So you can define more your own properties. You can go through states of the system and check if they are if there are deadlocks or no.
Yeah, session types have a different philosophy. I think that it's more like we have this tool that simple to use and has these properties built in. It's different, but yeah, definitely worth to have a look at that as well.
Thank you.